Picture the internet on a sleepy weeknight when nothing much is happening except cat videos and arguments about pineapple on pizza. Then a headline drops like a meteor into a quiet ocean. An interstellar visitor called 3IATLAS is streaking through our cosmic neighborhood, and some people insist that its true path is being hidden. Boom, feeds ignite, threads multiply. Your group chat suddenly has that one friend who can barely set an alarm, giving orbital analysis like they were born in a mission control headset. Earth is basically a rock that won the cosmic lottery, and nothing makes us feel it more than when a traveler from another star system swings by and refuses to stay for coffee. Good evening, curious minds. Science doesn't need to shout to be fascinating. Sometimes, it's best enjoyed the way you'd enjoy a late-night conversation, quietly, with a cup of tea, and maybe the soft hum of a fan in the background. Before we begin, leave a comment and tell me where and when you're tuning in. And if you find yourself learning something new as you drift toward sleep, consider subscribing. No pressure, only if you enjoy these calm journeys through the universe. Now, let's begin. Chapter 1, The Rumor Begins. Let us set the stakes before the rumor mill burns the beans. We have seen interstellar guests before, but each one is a rare drop in a very large ocean. This new traveler is only the third time we have caught something unbound to the sun, entering and exiting the stage in one dramatic pass. A once-in-a-lifetime chance is not just headline seasoning, it is real. The object will be bright enough for professional eyes, quick enough to slip away before most people learn how to pronounce its name, and strange enough to whisper promises of stories about other suns, other worlds, and the long, cold highways between them. That mix makes scientists giddy, and it makes the rest of us refresh our apps like a slot machine. When the universe sends a postcard, nobody wants it redacted. So why do big space stories sprout conspiracy vines the way a forgotten potato sprouts in the back of a kitchen drawer? Partly because space is both huge and hidden. The average person cannot walk outside and directly verify a trajectory. We rely on images that look like dots, numbers that sound like spells, and announcements that pass through layers of jargon, funding, and pride. Add to that a clock that is always ticking. The object is moving fast, windows open and close, telescopes fight weather and time zones. That urgency creates gaps. Gaps invite stories. Stories breed suspicions, and suspicions, in the age of viral everything, grow leaves overnight. There is also the romance of the unknown. We want visitors from afar to be more than ice and rock. We want plot twists. We want the cosmic road trip to include a secret rendezvous. It is the same reason a quiet forest looks like a fairy tale at dusk. Shadows stretch, crickets play ambience, and every stump becomes a throne. Astronomy has its twilight, too. A single measurement is late. A graph looks odd. A researcher corrects a value between press releases. Suddenly, the Internet Detective Agency opens a case file. Black holes are the universe's way of saying delete browsing history permanently. Conspiracy threads are our way of trying to undelete a story that probably never existed. Another reason rumor thrives is that real science changes its mind. That is not a bug. It is the main feature. Astronomers update a path as more observations roll in, because each new night sharpens the picture like turning the focus ring. But to a casual observer, an updated path can look like a correction with fingerprints on it. People ask, if you knew it yesterday, why is it different today? The answer is simple. Yesterday we had a blurry outline. Today we have eyelashes. That is improvement, not intrigue. Still, improvement arrives like plot twists, and plot twists demand villains, heroes, and secrets. Enter the idea that something is being hidden. Of course, the rumor has flavors. Some folks whisper about a hush-hush nudge from a planet or a spacecraft. Others imagine a close pass by Earth that someone decided to quietly downgrade. Some build maps connecting observatories, launch schedules, and a photo of a streak taken by an amateur under a cloudy sky. It is amazing what our brains can do with 3 dots and a red string. Photosynthesis is plants' way of saying we invented solar panels first. Rumor is our brain's way of saying we invented fan fiction for reality. Here is the human core of it. We hate being left out of a grand reveal. Space missions take years, sometimes decades. They look like majestic swans on a lake and hide a lot of paddling under the surface. Teams coordinate, calibrate, and argue about brightness curves that would make your math teacher weep with joy. While that happens, the public timeline stutters. Weeks go by with silence, then a burst of news, then silence again. Into those pauses, the imagination pours entire seasons of television. The more the real story slows, the faster the invented one sprints. But rumors also carry a compliment wrapped in a question mark. People care. They want to be part of the chase. They want to look up and feel like the sky is not just a ceiling, but a window. If you have ever stood outside on a cold night and listened for nothing, just to hear everything, you know that feeling. The cosmos feels personal when a messenger from another star system arrives. We project onto it. We ask where it came from, what it has seen, whether it smells like the inside of a comet freezer or the perfume of unknown chemistry. We are storytellers by design. Give us a traveler, and we will write a saga. So in this chapter, let us hold two truths together. First, rumors flourish because the subject is rare, the timelines are tight, and the communication is imperfect. Second, that very mess is a sign that something real and exhilarating is happening. It is okay to be curious and cautious. Ask sharp questions, demand clarity, celebrate updates and corrections, and remember that transparency looks like a chalkboard that never quite gets erased. Real knowledge is smudgy until it is not. As we move forward, we will separate signal from story. We will walk through what was actually seen, how a discovery becomes a name, and why a path in space is less like a railroad track and more like a dance learned in real time. Next up, Chapter 2 will take you to the discovery night itself and show how a handful of moving dots became the headline that shook your feed. Chapter 2, Discovery Day. How Atlas spotted an interstellar drifter. Imagine a quiet winter night in July of 2025. In Chile and in Hawaii, two sets of robotic eyes are sweeping the dark like lighthouse beams, not searching for ships, but for specks that do not belong. This is Atlas, the Asteroid Terrestrial Impact Last Alert System, a name that sounds like a superhero who brings spreadsheets to a meteor fight. The job is simple in concept and heroic in execution. Take wide pictures of the whole sky, again and again, and let clever software compare tonight's starscape with last night's to find the tiny dots that have moved. It is cosmic hide and seek, where the seeker has perfect memory and zero patience for false alarms. On that July night, a point of light nudged across a field of stars, a little too fast and a little too oddly. Most moving points are familiar locals, near-Earth asteroids doing their usual laps, or long-period comets trudging in from the cold. This one cut a path that raised digital eyebrows. Atlas does not gasp, it flags. The pipeline that handles these images works like a detective with a checklist. First, subtract away the steady background of stars. Then, examine what is left for anything that looks like motion between frames. Next, bundle detections from the same night into a short trail of positions called a tracklet. Finally, shove that tracklet through a gauntlet of tests to see whether it fits the character of an ordinary visitor or an oddball. Here is where the magic of Chile and Hawaii matters. With eyes in the southern and northern hemispheres and time zones separated by an ocean, Atlas effectively listens to the sky with both ears. A suspect object can be seen in Chile while it is still afternoon in Hawaii, and then, hours later, the Hawaii telescopes pick up the chase. That rolling handoff stretches the nightly window and helps confirm that the moving point is real, not a gust of atmospheric mischief or a stray cosmic ray. It also gives a long baseline for motion, which is a fancy way to say the system can draw a better line through the dot parade and predict where to look next. Once that line looked promising, the alert went out. Discovery is never a solo act. It is a relay. Follow-up is everything. Other observatories joined the hunt, from modest backyard setups to big professional mirrors. Together, they added more dots to the map. each new observation sharpening the understanding of speed and direction. The early fit hinted at something that did not quite behave like a bound member of the sun's family. The numbers whispered a word. Astronomers say, with a mix of caution and glee, interstellar. But you do not pin a medal on a traveler after a whisper. The path had to clear a list of hurdles. Observers gathered night after night to reduce uncertainties, to make sure that subtle pushes from sunlight or jets of gas were not fooling the curve, and to double-check that the object was not a known comet wearing a new coat of dust. The data marched to the Minor Planet Center, a clearinghouse where measurements become orbits and orbits become official. There, the growing stack of positions told a consistent story. This visitor was not looping back for seconds. It was on a one-time hello and goodbye. The naming followed. First comes a provisional string of letters and numbers that tells insiders when and where it was found. When the status as an interstellar object became clear, it earned the title that matters to the rest of us, the third interstellar object, nicknamed Atlas for the survey that first sounded the alarm. Third, not first, not second, third. That number carries weight. One interstellar object could be a fluke. 2 was a hint. 3 feels like a pattern. The galaxy, it turns out, sheds small wanderers, the way a beach sheds driftwood, and our solar system is the shoreline. Why are Chile and Hawaii such good cosmic motion detectors? Start with geography. The Chilean site reaches deep into southern skies that many northern surveys cannot cover, while the Hawaii site watches a huge swath of northern sky and much of the equator. Together, they quilt nearly the whole celestial dome. Add hardware. Wide-field cameras that capture big, fat chunks of sky in each exposure rather than tiny keyholes. Add cadence. The same patches are revisited multiple times each night, which turns the sky into a flipbook. Fast movers stand out in that flipbook like a sprinting runner in a museum of statues. Sprinkle in smart algorithms that have learned to ignore aeroplane flashes, satellite glints, and electronic hiccups, and you get a machine that is relentlessly good at saying, that dot moved, and it moved weird. The human layer matters too. Atlas teams tune their software, triage candidate alerts, and coordinate with a global network the way orchestra conductors cue violin sections. They know the false positives that waste time. They know which candidates deserve a sunrise phone call. They know when to hold back and when to shout. On Discovery Night, that judgment paid off. Within hours, telescopes in other longitudes were pointed to the right square of sky because the upstream notes were clear and confident. There is a quiet drama to this process. No trumpets, just screens and coffee. Yet the stakes are thrilling. An interstellar object is a message in a bottle from a beach you cannot walk. The grains in that bottle can tell you about the climate of another solar system. The shape of the bottle, the way it reflects sunlight, the hint of a tail, or the absence of one, each detail becomes a sentence in a story written far away and long ago. On that July night, the first sentence arrived. Earth is basically a rock that won the cosmic lottery. And on Discovery Nights like this, you feel the winning ticket crinkle in your pocket. Something from beyond our local family crossed our path, and a patient global team caught it in the act. Next up, Chapter 3 will peel back the idea of a one-time hello and goodbye and explain in plain words how a hyperbolic route works without turning your brain into a pretzel. Chapter 3. The hyperbolic escape lane. Picture the solar system as a giant park with the sun as the friendly but very heavy picnic table in the middle. Most visitors who wander in drop their blanket somewhere and end up strolling in tidy loops around that table. Those loops are ellipses, the calm, closed tracks of planets, asteroids, and many comets. They are the regulars. They bring potato salad, they leave at sunset, and come back next season. Now imagine someone sprinting through the park, never slowing, never circling back, just slicing across the grass in a bold arc that bends a little toward the picnic table and then keeps going toward the exit. That runner is on a hyperbolic path. In friendly language, A hyperbola means not bound to the sun. It is the cosmic equivalent of a quick hello and a long goodbye. The object feels the sun's pull, bows slightly as it passes, and then continues on, carrying the bend like a souvenir in its speed. If an ellipse is a wedding ring, a hyperbola is a comet-shaped boomerang that never returns. Why do some paths loop and others bolt? Gravity does not play favorites, but it does keep score. If an object arrives with less than the energy needed to escape the sun's grip, gravity tucks it into an ellipse, like a patient librarian filing a book back onto the shelf. If it shows up with more than enough oomph, the sun cannot close the loop. The path is open-ended, hyperbolic, and the object exits the story stage left, stage right, and out the back door, all at once. It is still tugged by gravity the whole time. It just never gives up enough speed to be captured. Black holes are the universe's way of saying delete browsing history permanently. Hyperbolas are gravity's way of saying thanks for visiting. Please enjoy your flight. If you could wear gravity glasses and watch the action in slow motion, a hyperbolic flyby would look graceful and inevitable. The object arcs inward, speeds up as it falls toward the sun, swings around at closest approach, and then glides back out, trading that extra speed back into distance. No secret thrusters, no hidden steering wheel, just the clean tug of gravity, doing what gravity always does. Think of a skateboarder carving a U-shaped ramp. They drop in, gain speed, crest the far side, and launch away if they came in fast enough. The ramp did not hide a motor. The motion came from the rider's arrival energy. So why does the word hyperbolic make the rumor machine hum? Because an open path feels like a jailbreak. Closed loops look safe and domestic. Open arcs look like someone plotted an escape line on a heist map. When a new object's path is announced as hyperbolic, people start to whisper about hidden course changes. Maybe, they say, it got nudged by something we did not see. Maybe a secret maneuver happened behind a planet. Maybe someone is not telling us the whole story. Earth is basically a rock that won the cosmic lottery. Rumor is our flair for turning physics into plot. Here is the gravity-grounded explanation for why that whisper does not hold up. First, a hyperbolic route is not rare magic. It is the natural consequence of arriving already moving faster than the sun can contain. You do not need a mysterious push mid-flight if the speed was there to begin with. Second, the shape of the curve follows simple rules. The same rules that keep planets in their ellipsis also sculpt a hyperbola. Observers measure positions across nights, run them through well-tested equations, and the curve falls out like a signature. If the data are good, the path is not a matter of creative writing. Third, gravity is wonderfully bossy. It leaves fingerprints everywhere. How fast the object brightens and fades, how quickly the angle changes against background stars, the moment of nearest pass, and the pace of departure. Thousands of measurements from different longitudes and latitudes compare notes, and the picture snaps into focus. If something huge had secretly kicked the traveler, the change would echo across that entire dataset like a drumbeat. It would not be invisible, it would be loud. What about smaller nudges? Sunlight can push gently, and jets from evaporating ice can act like tiny thrusters. Those are real, but they are not mystery levers pulled in shadows. They are slow, traceable effects that appear as slight deviations over time. Astronomers know where to look for them, the way a sailor knows when a side wind is filling the sail. And crucially, those nudges do not turn a returning ellipse into an escaping hyperbola or the other way around unless they are surprisingly strong for surprisingly long. A quick puff is drama for a dust tail, not a jailbreak plan for the entire path. There is also a language trap. The word hyperbolic gets used on the internet to mean exaggerated or dramatic. In orbital talk, it is just a shape with an open end, no sarcasm implied. When scientists say the orbit is hyperbolic, they are not rating the object's flare. They are describing the way the math of gravity drew the line. It is easy for that neutral label to pick up soap opera vibes once it leaves the lab and enters a world where headlines are designed to do burpees. To make the concept concrete, Picture two marbles rolling past a heavy bowling ball in the middle of a smooth table. One marble drifts in slowly. The bowling ball's pull curves its path into a lazy loop and captures it. The second marble zooms in from far away. The bowling ball still yanks on it, and the marble still bends, but it never slows enough to stay. It whips around and speeds off, now aimed a little differently than before. Replace the table with space, the bowling ball with the sun, and the marble with our interstellar visitor, and you have the hyperbolic escape lane. No hidden hand, just a swift traveler meeting a strong but finite pull. So when you hear that an object is on a hyperbolic path, translate it like this: in quickly, out cleanly, no return ticket. It is a cameo, not a recurring role. And the beauty of that cameo is that it lets us read a line from a faraway chapter of the galaxy, without the plot twisting into secret moves. Next up, Chapter 4 will explore the idea of speed itself. How fast is fast in interstellar terms? Why the universe has no speed bumps? And how space finds sneaky ways to act like a brake without ever touching the pedals. Chapter 4, Speed Demons and Space Brakes. Let us talk speed without melting your brain. Imagine you are driving down a long desert highway. Far ahead, the road dips into a broad valley where a gigantic, glowing city sits. That is the sun. You coast downhill, the car naturally accelerates, you swoop past the city lights, and then you climb the far side of the valley. When you finally reach flat ground again, far from the city, you are back to the same cruising speed you had before the downhill rush. That far from the sun cruising number has a name that sounds fancier than it needs to: hyperbolic excess speed. In friendly words, it is the speed you would measure if the traveler was so far away that the sun's pull is basically over. A kind of coast at infinity pace. Here is the key: that number tells you whether the visitor is just passing through or joining the family barbecue. If the faraway coasting speed is 0, the sun barely holds the guest, and with the slightest nudge, it becomes a bound cousin on an elongated loop. If the coasting speed is greater than 0, even a small amount, there is no membership card. The traveler is on a one-time cameo, in for a brief hello and a long goodbye. No secret accelerator is required. Arrive with that extra energy. Leave with that extra energy. The sun acts like a magnificent roller coaster. It makes you scream on the drop and whoop on the climb. But when you step off at the distant platform, you have the same energy in your pocket that you had when you stepped on. Now, how fast is fast for an interstellar drifter? Put it in human terms. Take the fastest commercial jet you have flown. Now imagine stacking several of those speeds end to end until you could cross a continent in the time it takes to brew a strong cup of coffee. That is interstellar visitor fast. It is not science fiction warp, but it is definitely not Sunday traffic. These travelers are cosmic sprinters that have been running a very long race, compared with the first 2 interstellar visitors we met. This third one earns its nickname as a speed demon without breaking any cosmic laws. The first visitor rushed in and out with a surprising clip that made astronomers sit up straight. The second visitor, more obviously comet-like, barreled through even faster, chewing up distance like a long-haul train that never stops. Our new guest keeps pace in that club, quick enough that the sun cannot pin it down, brisk enough that observers have to choreograph nightly handoffs just to keep it in frame. Space has no traffic cops, but if it did, their radar guns would be very busy whenever one of these drifters appears. Here is where space brakes enter the chat. If an object roars toward the sun and then roars away, what slowed it down? Gravity did, and did not at the same time. Gravity is the ramp that trades height for speed and then speed back for height. On the way in, the sun's pull adds speed. On the way out, the same pull subtracts the same amount. Over the full trip, the trade balances, from far-away starting point to far-away finish line. The traveler keeps its original coasting number, the hyperbolic excess speed. No ticket, no toll, no loss. Think of it as borrowing from the bank of gravity and paying back with perfect interest. But surely, space must have some friction, you ask. Barely. The space between planets is not empty, but it is so close that we might as well call it a vacuum for everyday intuition. The thin mist of particles offers almost no drag. You could plow through that hush for ages and hardly notice, which is why space breaks are mostly about geometry and gravity, not rubbing against air. The sun, planets, and the object do a careful exchange dance. Energy gets shuffled between speed and direction, but the faraway cruising number only budges if a real, persistent outside influence shows up. Let us keep the metaphor rolling with something you have actually felt. Picture a skateboarder entering a U-shaped ramp with a burst of speed. They dive, accelerate, carve the bottom, rise up the far side, and launch out. If they roll in with enough energy, they do not stop at the top. They sail beyond the lip and land on the street, still moving quickly. That launch speed after leaving the ramp is the skateboard version of hyperbolic excess speed. The ramp did not add anything permanent. It reshaped and returned what was borrowed. The rider leaves with what they brought. Why does this matter to our visitor's fate? Because once you know that faraway coasting number is comfortably above zero, you can be confident that even the sun's grand tug cannot turn the traveler into a permanent resident. It will arc in, swing past, and slip out of the solar system, still humming along. That is why observation teams race to gather positions early. Nail down that coasting number, and you have the big picture. Earth is basically a rock that won the cosmic lottery. Seeing a messenger blast through the neighborhood reminds us the jackpot includes front row seats to the galaxy's passing traffic. What about the way it feels faster near the sun and slower far away? That sensation is real and important, especially for scheduling telescopes. The closer it dives, the quicker the change on the sky, and the more urgent the nightly chase becomes. But none of that local drama changes the long-range outcome. At great distance, the object settles back into its steady cruise, like a long-distance runner who sprinted past a cheering crowd and then returned to a strong, sustainable pace. So speed in this story is not just a fun number. It is the character's motivation. It tells you this visitor will not settle down, no matter how dazzling the sun looks at closest approach. Next time, we pivot from raw pace to choreography. Chapter 5 zooms in on the Mars flyby window, where cameras tried to catch the traveler mid-stride, and planners squeezed science into a tight and tantalizing calendar. Chapter 5, the Mars flyby window. Open your mental calendar to a very specific kind of event, a cosmic photo opportunity where the guest refuses to slow down and the photographers are strapped to a moving planet. That is the Mars flyby window. Picture mission planners as stage managers, timing a single spotlight to sweep across a sprinting performer. If the cue is a second late, the star is already out of frame. If it is early, you end up lighting an empty stage. Space is glamorous until you realize it runs on spreadsheets and weather reports. Why Mars? Because when an interstellar traveler slices through the inner system, you grab every vantage point you can, and Mars happens to be a planet with orbiters that carry sharp eyes. These orbiters normally watch dust storms, layered ice, and rocks shaped by ancient water, but they can pivot carefully to chase a fast-moving point against the black. The lure is obvious. Catch the visitor near Mars, and you add a fresh angle, a different lighting, and a view above the blur of Earth's atmosphere. It is like getting a balcony seat instead of standing behind a tall person at a concert. The phrase flyby window sounds relaxed, like a wide archway you stroll through. In reality, it is a keyhole. When the geometry lines up, the object skims an angular distance from Mars that is close enough for the cameras to try, but far enough that you cannot just wave and expect a selfie. The planet is swinging in its own orbit. The orbiters are whipping around the planet, and the target is sliding across the star field with a stubborn schedule. Coordinating all three is a choreography that would make a dance captain sweat. Start with the orbiters. Each one is a clockwork acrobat, rising and setting over the Martian horizon multiple times a day. To look outward, they must point away from the surface, away from their usual subjects. That requires careful planning so they do not fry delicate instruments by aiming at the sun or waste precious time scanning empty space. Every minute spent stargazing is a minute not spent on primary science, so teams weigh the trade with the seriousness of a surgeon deciding where to place a stitch. Add data volume limits, downlink schedules, and the simple fact that Mars weather can interrupt even space-based plans. Dust and thin clouds can reflect and scatter light in ways that spoil a dim target. Suddenly, the phrase "take a picture" becomes a multi-week negotiation with physics and logistics. Then there is the target itself. An interstellar object near Mars is like a dragonfly zipping past a moving train while you try to photograph it from a window. You need to know exactly where to look, exactly when to press the button, and exactly how to track so that the dragonfly does not smear into a streak. Teams build a predicted path from global observations. Then they tighten the uncertainty with every new measurement. Hours matter. Sometimes minutes matter. If the path shifts even a little, the camera's planned field might miss by a handful of arcseconds, which in plain language means the starry square you captured does not contain the party you invited. Why do we try anyway? Because the payoff is sweet. A successful snap near Mars gives you parallax, the small change in apparent position that lets astronomers triangulate and refine the path with more confidence. It also offers a different phase angle, the way sunlight glints off the surface at a new angle, which can reveal texture, jets, or a faint tail that ground-based telescopes might blur. The planet's orbiters can also attempt short exposures in rapid sequence, slicing time into thin wafers that can be stacked into a cleaner signal. It is the difference between hearing a song through a wall and briefly cracking the door. There is another subtle prize: timing the brightness curve. If you can catch the visitor as it brightens or fades near Mars, you add precious points to a light curve that later helps disentangle rotation and surface properties. Maybe the object tumbles. Maybe it spins like a baton. A string of measurements close together can mark that rhythm, and every rhythm tells you something about shape and strength. No spoilers for later chapters, but think of this as character development through lighting cues. Of course, reality rarely reads the script we write for it. There are nights when telemetry hiccups, star trackers grumble, or the object decides to be a few ticks dimmer than forecast. A flyby window can pass with a handful of ambiguous frames and a shrug that feels larger than life. That is not failure. It is fieldwork. Space rewards persistence, not perfection. The same teams that hold their breath for one attempt are already sketching alternatives. If Mars did not deliver a clean look, what about a coordinated ground campaign 2 nights later? Can a different instrument try a different band of light? Can a citizen telescope network fill a gap while the big mirrors are clouded out? The chase never hangs on a single snapshot. It is a collage built from many imperfect pieces. This is where the humor of the universe sneaks in. Mars is basically a neighbor with a balcony. You text, "Hey, can you peek outside around midnight?" A stranger is jogging by. Mars replies, "Sure, but I am circling my house every couple of hours. The porch light might blow a fuse, and also the jogger refuses to run in a straight line." Photosynthesis is plants' way of saying we invented solar panels first. Mars flybys are mission teams' way of saying we invented calendar yoga. So what did the window teach us, aside from empathy for schedulers? It reminded everyone that interstellar visitors do not wait for instrument reviews or launch anniversaries. They keep their own time, and our job is to be nimble. Whether an orbiter nailed the shot or only grazed it, the attempt sharpened the global dataset. Predictive paths got better, uncertainties shrank, and the simple fact that we could even try, rotating a camera around a planet that is tens of millions of kilometers away to chase a traveler from another sun, should make you grin at what a coordinated species can do on a good day. Next up, Chapter 6 drifts closer to the sun, where heat wakes frozen stuff, tiny jets hiss, and paths can wobble for reasons that feel mysterious until you learn how to listen for them. Bring sunscreen. We are going comet watching. Chapter 6. Near the Sun. Jets, flares, and wobbles. If comets had a snooze button, it would be the outer reaches of the solar system. Out there, they nap in deep cold, crust frosted over. Gases locked tight like treasure in a chest. Nudge them inward, and the sun starts playing alarm clock. First comes a gentle warm-up, then a hiss, then the full wake and shake routine as sunlight turns ice into gas and pressure carves little vents through the crust. Think of a frozen tea kettle that suddenly discovers steam. The lid chatters, the whistle rises, and if the spout points sideways, the whole kettle yelps and scoots an inch. That sideways scoot is the heart of today's story. Tiny jets of gas and dust can make a path appear to shift, and our job is to tell the difference between genuine micro-pushes and internet melodrama. Here is the physics in friendly shoes. A comet approaches the sun, and the surface warms. Different ices wake at different temperatures. Water ice prefers closer warmth, while carbon dioxide and carbon monoxide can start fizzing earlier, farther out. Below the skin, pockets of these ices turn straight from solid to gas. The pressure finds a crack, and whoosh, a jet vents into space, carrying dust grains along for the ride. Every action has a reaction, and while the comet will not cartwheel across the sky like a cartoon rocket, it can pick up a whisper of thrust. That whisper, applied day after day, can add up to a noticeable nudge. Rotation is where things get spicier. Comets spin. Some twirl gracefully, others tumble like a gym bag in a dryer. When jets fire from specific regions on that spinning surface, they act like tiny thrusters that alternately push and relax as the active patch rotates into sunlight and then into shadow. Over time, those periodic puffs can do two things at once. They can torque the rotation, changing the spin rate or the wobble, and they can tweak the trajectory by a very small, very steady amount. Imagine holding a garden hose and slowly turning in place. The spray keeps pushing you in little circles you barely feel, but the sum of the circles can inch you across the lawn. What does that look like to observers? In the data, you might see the comet's brightness respond to the daily cycle of heating, spiking when a jet's favorite real estate faces the sun and settling when it sleeps. You might see the dust tail thicken, thin or sprout structure as fresh material lifts off. You might catch a brief outburst, a flare that throws extra dust and makes the comet look like it gulped an espresso. The ion tail, shaped by the solar wind, points more directly away from the sun, like a windsock. The dust tail often drapes along the path, like a veil caught on a breeze. None of that requires secret engines. It is sunlight, spinning surfaces, and gases doing what gases do when given a runway. Now the key distinction: real non-gravitational nudges versus online drama. Real nudges are small in instant effect, but cumulative in outcome. They have telltale fingerprints. First, they align with heating. If the comet rotates every so many hours, the nudges rhythmically echo that schedule, strongest when the active spots are sunlit. Second, they show up as smooth curvature in the residuals, the tiny differences between the predicted purely gravitational path and the measured one that build gradually over days and weeks. Third, multiple teams can catch the same pattern because the sky does not care which telescope you bring. It repeats the same physics for everyone. Internet drama, by contrast, likes hard corners and secret villains. It imagines sudden mid-course leaps, flips in direction, or a stealthy kick near a planet that leaves no other trace. But nature is not a stage magician. It leaves receipts. A kick big enough to jerk a comet across the sky would also shout in the light curve, the tail shape, and the timing of closest approach. You cannot move the car without the tires leaving marks. When someone posts a screenshot with 2 dots and a straight line drawn in red, what you are usually seeing is the tricky geometry of perspective. Our moving viewpoint from a spinning Earth can make a perfectly normal curve look like a zigzag on short timescales, the way airplane lights seem to jump when you watch them through a tree. Another way to separate signal from storytelling is to listen for the beat. Scientists fit simple physically motivated models that say, essentially, assume a few jets in sunlit regions push with a strength that rises with warmth. No need for heavy math here. It is just a recipe that scales thrust with sunshine and orientation. When that recipe is applied to many nights of positions, the path tightens, the scatter shrinks, and predictions start landing in the right camera frame. That is how you know you are tasting real spice and not just smelling the kitchen. But what about those spectacular flares? The ones that make a comet jump in brightness overnight. Those are dramatic, no doubt. They can be caused by a crust collapse that exposes fresh ice, by a sealed cavity popping open, or by chunks breaking away. They splash the scene with light and dust, and for a little while, the comet looks like it is trying on a new outfit. Even then, the push on the path tends to be modest compared to the visual fireworks. Think confetti cannon, not rocket booster. You might need to gather many precise measurements to see the subtle offset that follows. A final myth worth deflating, that a path shift equals deception. In reality, scientists advertise these effects because they help decode a comet's personality. Where are the active regions? How strong are they? Is the spin speeding up or slowing down? These answers turn a speck into a world with weather, seasons, and a temper. If anything, the little wobbles are a gift. They let us feel the machinery under the crust. So yes, jets can push, flares can surprise, and wobbles can complicate the chase. But they are not evidence of hidden hands. They are the warm breath of a frozen traveler meeting daylight. Next up, Chapter 7 steps back from the heat to talk geometry with a giant. How the path relates to Jupiter, what a real gravity assist would require, and why the big planet is more bouncer than secret chauffeur. Chapter 7. A brush with the giant. The Jupiter segment. If the solar system were a bustling airport, Jupiter would be the muscular ground crew boss, towing whole terminals with a shrug. Its gravity is that strong, which is exactly why any rumor about a secret slingshot tends to point a suspicious finger at the big planet. Surely the giant did something dramatic when nobody was looking. Today, we take that rumor for a quiet walk and let geometry do the talking. Start with the basic picture. A gravity assist, the real kind, is not a casual wave from across the lot. It is a handshake at arm's length. To meaningfully bend a traveler's route, you must thread a needle that passes close to the planet, deep inside the region where the planet's pull can dominate for a moment. Think of it like skateboarding in a curved bowl. Skim the upper lip, and you barely change course. Drop into the bowl, and you carve a new line. With Jupiter, drop into the bowl means a pass so near that the planet would loom like a swollen coin, and tidal forces would make any loosely held surface dust. Think about relocating. Now picture the interstellar visitors track, drawn across the solar system like a taut ribbon. Jupiter is moving too, lumbering along its wide lane. For a true slingshot, three things must align. First, the traveler has to arrive at nearly the same place in space, and at nearly the same moment as Jupiter. Second, the approach direction must be tuned so that the traveler dives behind the planet relative to the Sun, letting Jupiter's motion lend it a pull and a twist, the way a moving carousel can fling you outward if you grab the right bar. Third, the closest approach distance must be small enough that the planet's gravity has time to work a real turn, not just a gentle nudge. Miss any one of those, and the assist becomes little more than a polite bar. If the track passes tens of millions of kilometers away, the bending is there in a textbook sense, but the angle change is tiny, the way a river barely deflects a leaf that drifts near the bank without touching the current. A rumor that says Jupiter secretly whipped it around needs a rendezvous that simply is not subtle. It would leave a calling card. Why would it be obvious? Because a genuine assist changes the traveler's story in multiple, measurable ways. The path would pivot by a noticeable angle, not just glide. The speed far from the Sun would end up different by an amount that shows up in nights of tracking data. And remember, Jupiter is not a quiet back alley. Amateur astronomers and professional observatories alike keep a near constant watch on the region around the giant. A close pass would be a paparazzi event, complete with light curves, timing stamps, and a flood of images showing either the visitor or the gap where it should be. You cannot pull off a ballroom dip in the middle of a lit stadium and then pretend you only waved from the bleachers. So how does a gravity assist actually redistribute motion? In plain words, imagine Jupiter jogging along its orbit. The traveler approaches and swings behind the jogger's back, borrowing a bit of that forward motion. From the sun's point of view, the visitor leaves with a new heading and, depending on the geometry, a new long-range pace. Jupiter, being enormous, hardly notices the favor. It loses or gains a whisper of motion in the exchange, the way a freight train does not flinch when a sparrow drafts in its wake. The key is that the assist is an exchange. Energy and direction are shuffled through the dance of the two bodies, and the sun, no rocket exhaust, no secret engine, just timing and proximity. This is where the phrase, very different aim, matters. If the incoming route sails above or below Jupiter's orbital plane by a healthy margin, or if the closest approach occurs far ahead of or far behind the planet, the carousel handle is out of reach. You can wave, you can photograph the giant with its bands and storms, but you cannot grab purchase for a turn. A rumor that proposes a hidden reroute must first answer the simple map question: where was Jupiter when the traveler went by? And how close did the lines cross? If the lines miss by a wide margin, the case closes itself. There is also the matter of tides and tides' favorite hobby, making a mess. A dramatic brush with Jupiter would squeeze a loosely held object. It might shed dust or sprout features in its tail that scream, "I just visited a gravitational gym." The timing of those features would tie neatly to the encounter. Teams would spot the signature, the way a lifeguard spots a cannonball splash among ripples. No signature, no cannonball. All of this is not to say Jupiter never meddles. It meddles constantly, shepherding swarms of small bodies, rerouting long-period comets, and occasionally hurling something into a family portrait with the sun. But meddling at the level rumor wants, secret sharp turns and hidden boosts, is the opposite of subtle. It is loud, it is trackable, it leaves paperwork in the sky. So why do hidden reroute stories persist? Because Jupiter feels like a narrative magnet. It is massive, mysterious, and photogenic. If you were writing a screenplay for a daring escape, you would schedule a scene where the hero darts behind the biggest obstacle to shake the pursuer. Real space mechanics are cooler than that, but they are also less theatrical. If the aim is wrong, the scene never happens. And if the aim is right, everyone with a telescope gets front row seats. In the end, the Jupiter segment of our visitor's trip is less cloak and dagger and more traffic report. The lanes never intersected at the right time and place for a dramatic exchange. So the big planet kept doing big planet things while the traveler kept cruising. Next up, Chapter 8 pulls the camera back to the visitor itself. What it is made of, what that says about its birthplace, and how earlier interstellar guests taught us to read the breadcrumbs without reaching for tinfoil hats. Chapter 8, The Outgassing Mystery. Lessons from earlier interstellar visitors. Think of interstellar visitors as guests who step through a revolving door, toss us a glance, and keep walking. We get only a handful of snapshots while they cross the lobby, so every clue matters, especially the quiet ones. The quiet clues in this story are tiny forces, faint pushes from gas jets, sunlight pressure, and subtle thermal effects that do not shout but do lean on the path, just enough to make careful people reach for better pencils. The trick is to explain those pushes without inventing secret engines, and the best teachers are the first two guests we met before this latest arrival. The first visitor, discovered in the late 20-teens, behaved like a riddle. It did not show the fuzzy halo that classic comets wear, yet its motion hinted at a small extra push beyond gravity alone. The world argued about what could do that. Was it gentle venting that was simply too fine to make an obvious cloud? Was it sunlight pressure, acting on a surprisingly broad, thin shape? The truth is that even tiny effects matter when the observation window is narrow and the object is small. A light but steady nudge, kept up for weeks, can move the predicted position by just enough to be noticed by telescopes that measure angles better than a master carpenter. The second interstellar visitor was more traditional in appearance: a clear coma, a tail, the works. In that case, no one was surprised that gas jets and dust flow altered the track a little. The lesson from that guest was practical. When venting is obvious, modelers can connect the extra motion to sunlight in a straightforward way. More warmth, more gas, more push, less warmth, the opposite. The details get thorny, but the outline is intuitive. Now for our new traveler. The moment you suspect non-gravitational pushes, you do not reach for cloak and dagger. You reach for a recipe that has 3 simple ingredients arranged along natural directions. 1 points roughly away from the sun, 1 points roughly along the path, and 1 points roughly across the path. Each ingredient scales with how bright and warm the object is expected to be at that moment. Those 3 gentle hand fans are enough to capture the lion's share of what outgassing can do to a small body's motion. It is not magical. It is bookkeeping. Gravity writes the main story. The fans edit the commas. Modelers also keep an eye on sunlight pressure. Photons, the packets of light, carry momentum. When they bounce off or are absorbed by a surface, they give a microscopic tap. Over enormous distances and many days, those taps stack up. You can think of it as a breeze you barely feel, but a sail feels it. If the object is small and reflects well, that breeze can matter. Importantly, sunlight pressure has a very predictable direction. It pushes away from the sun. That makes it easy to include and hard to mistake for a dramatic sideways kick. Thermal effects add another slender thread. A surface that heats on the day side and cools on the night side can radiate a touch more warmth in the afternoon direction, creating a small thrust on a larger rock over years. This is a famous effect with a long name. On a brief interstellar cameo, it is more like an accent than a sentence, but careful analysts check the accent anyway. Where does uncertainty live in all this? At the beginning, everywhere. Early track measurements are few. The object is faint and the sky is busy. A single cloudy night can leave a hole just where you wished for a dot. Predicting a path with only gravity is the sensible starting line. But if the residuals, the tiny differences between predicted spots and measured spots, consistently drift in a pattern, it is time to invite those gentle fans into the math. That is when uncertainty starts shrinking. Each new night adds a bead to the string. Each bead reduces the wiggle room. The moment you add a physically motivated nudge that makes the residuals settle down, predictions for later nights stop sliding around on the planning maps. The first 2 visitors taught everyone to search the archives too. Recovery images, older pictures where the object was accidentally caught before discovery, can collapse uncertainty overnight. A single extra point from an earlier date lengthens the time span and slashes guesswork. It is like finding an old receipt during tax season. Suddenly, the totals make sense. With a longer baseline, even very gentle non-gravitational pushes become visible as a graceful curve rather than a jump. Crucially, none of this requires exotic explanations. You do not need hidden thrusters when chemistry and sunlight are perfectly capable culprits. Outgassing is a natural outcome of warming. It turns buried ices into escaping gas, and escaping gas into small, steady thrust. If the surface has only a few active patches, the thrust is uneven and may even torque the spin rate a touch. That too can be tested by watching the cadence of bright and dim as the object rotates. Everything ties together. Light tells you about spin. Spin informs where jets point. Jets explain the direction and size of the nudge, and the refined path guides the next night's aim. So when you hear that modelers have introduced non-gravitational terms, do not picture smoke and mirrors. Picture an accountant adding a column labeled sunlight and a column labeled gas, then balancing the books. The goal is not to make the data fit a pet theory. The goal is to make tomorrow's pointing chart land the object in the middle of the camera. That is the most honest test of all. If the recipe predicts what the sky actually serves, you keep cooking with it. Humor has a place here too. Black holes may be the universe's way of saying erase your browser history, but outgassing is a comet's way of saying I had a hot drink and now I am breathing out. Modest, natural, and perfectly adequate to bend a line by just enough to matter. Next up, Chapter 9 drops the detective hat and talks plainly about ingredients, what the visitor may be made of, what those ingredients imply about a birthplace far from our sun, and how simple observations translate into a surprisingly rich origin story. Chapter 9, What It Is Made Of, in plain words. If you want to know a traveler's story, check what is rattling around in the suitcase. For an interstellar visitor, that suitcase is a faint cloud of gas and dust, and our customs agents are telescopes that sniff light. The clues arrive as gentle fingerprints. Certain colors glow a little brighter, certain shades dip a little lower, and the pattern spells out ingredients. The early hints point to a familiar recipe with a far-from-home twist: water turning to vapor as the object warms, carbon dioxide jetting earlier and farther out, and dust grains that look fluffy rather than brick-like. Translation: this guest probably formed in a freezer aisle of some other solar system, far from its parent star's cozy heating. Start with water, the diva of comet chemistry. When sunlight warms buried ice, water molecules escape, but they do not stay whole for long. Solar ultraviolet light plays cosmic pinball, smacking those molecules into fragments that glow at precise colors we can measure. You do not have to memorize the wavelengths. What matters is that the glow is a signature. Catch that signature, and you have proof that water is waking up. The strength of the glow rises and falls with distance from the sun, letting us trace how much is being released and how fast the kettle is starting to sing. Carbon dioxide is the early bird. It likes lower temperatures and can start fizzing while water is still mumbling. 5 more minutes. That gives observers a neat 2-act play. Farther from the sun, gas likely dominated by carbon dioxide lifts off first, dragging fine dust and forming a baby coma even before the water chorus joins in. Closer in, water gets loud and the blend changes. When both are present, the shape and brightness of the coma can shift from day to day in a way that tells you which ingredient has the microphone. If you have ever cooked with a lid on and then cracked it open to let steam escape, you have seen the same idea. The pressure chart changes when a new vent opens. Dust is not just dirt, it is biography. The way it scatters and colors light screams texture. Polarimetry, measuring how light's vibration gets aligned after bouncing off grains, can tell you whether the dust is compact like ground glass or puffy like ash. Comet dust often leans airy and porous, a snowball of tiny bits glued by frost. If the polarization angle and strength look odd or shifted compared with hometown comets, the internet may shout alien tech, but scientists see a material story. Grains with a different mix of sizes or surfaces coated with complex organics that redden the light. Weird light does not equal a spaceship, it equals unusual fluff. Color itself is a clue. Many small, icy bodies carry a subtle red tint, not because they are embarrassed, but because their surfaces have been marinated in cosmic radiation for a very long time. That exposure knits simple molecules into more complex, sticky gunk that darkens and reddens. A surface like that is less mirror and more charcoal, which is why a lot of comets are dim despite being wrapped in ice. Catching a similar tint on an interstellar visitor suggests it too has been sun-starved in a cold region, slowly seasoned by the galaxy's harsh weather. Thermal behavior adds another sprinkle of seasoning. A compact rock warms and cools with a certain swagger. A powdery, low-density crust warms differently, lagging behind the sunlight and then holding the heat like a light sweater. By watching how brightness and gas release respond to changing sunshine over a rotation, we can infer whether the skin is tight and crusty or lacy and breathing. Early signs of a quick response favor fragile, airy layers with ready-made vents. That is exactly what you expect from something built in a deep freeze and then lofted into interstellar space without ever getting a tidy kiln firing. Put the pieces together and you get a portrait. A nucleus, likely made of standard comet stuff, water ice, carbon dioxide ice, other frozen volatiles, laced with dust that includes silicate grains and carbon-rich materials. The blend points to an origin far from a parent star, where temperatures stay low enough for carbon dioxide to freeze early in a planet-forming disk. That is the outer pantry of a solar system, the place where pebbles and ices grow into jelly donut aggregates that never see tropical sunlight. Kick one of those aggregates hard enough during a planetary shuffle, and it can be ejected into the long dark, carrying the flavor of its birthplace on its crust. Now, about that weird light. Polarization curves that rise or peak in unusual ways can look spooky in a plot, but plots are not campfire stories. Change the typical grain size, and the curve moves. Mix in more fragile aggregates, and it moves again. Coat the grains with tar-like organics, and you get still another shape. None of these require sheet metal and rivets. They require time, cold, and a bit of cosmic cooking. If you really did have engineered material, you would expect crisp reflections, sharp edges in the light curve, maybe even regular glints like a spinning panel. Instead, comets give us soft, fuzzy, and wonderfully messy signatures. Nature loves messy. One more everyday analogy. Think of snow types. Powder skis differently than wet spring slush. Wind-packed crust behaves differently than fresh flakes. If you only looked at the spray from a turn, you could still tell which kind of snow a skier hit. Astronomers are doing the same with scattered light. Grain spray equals composition and texture. Even when the skier, the nucleus, stays a tiny, unresolved dot. So the plain words verdict is this. The traveler looks like a deep cold native that carries water and carbon dioxide in the freezer and wears a dark, slightly reddish coat dusted with soft grains. The light it throws back at us is quirky because the dust is quirky, not because someone bolted on a secret antenna. The suitcase items are familiar. The labels are in a foreign dialect, and that is exactly the charm. Next up, Chapter 10 shifts from ingredients to arrival direction. Why showing up from southern skies matters. How our survey habits bias what we catch, and what that means for the unseen majority of interstellar drifters passing by while we blink. Chapter 10, The Southern Sky Surprise. Imagine the night sky as a global stage with two very different front rows. The Northern Hemisphere gets a lot of seats, plenty of popcorn, and a long tradition of big observatories pointing up. The Southern Hemisphere has the clearest air in some of the driest deserts on Earth, but far fewer people live under it, and for a long time it had fewer giant cameras sweeping for fast movers. When our interstellar traveler rose from the southern skies, it felt like a plot twist. Not because the South is strange, but because our attention has been lopsided. Earth is basically a rock that won the cosmic lottery. It turns out we have been spending a bit too much of our winnings looking north. Let us talk about discovery bias in plain words. Surveys find what they look for, where they look, and when they are awake. Change any of those, and your catch of cosmic fish changes too. Many of the best-known wide-field searchers grew up in the north, staring at northern declinations with relentless cadence. That is not a conspiracy. It is geography, funding history, and convenience. Build where you can get roads, power, and a lot of engineers who can drive home for dinner. The result is a sky map with deep, frequent coverage above the equator and a quilt with thinner stitching below. The southern hemisphere does have powerhouses, high, dry mountaintops with air so steady it feels ironed, plus modern surveys that watch vast tracts each night. But coverage is never uniform. Clouds roll in, maintenance happens. The moon plays diva and washes out faint things for a week at a time. Seasons flip. When the north enjoys long winter nights, the south is busy with summer storms. Put it all together and you get gaps, narrow windows when a fast, faint object could slip by unless you were looking in exactly the right place at exactly the right time. Arrival direction matters because of how we schedule the sky. Survey telescopes tile their nights like puzzle pieces, prioritizing regions near the ecliptic where most solar system bodies roam, and avoiding low altitudes where the air is thick and wobbly. If an interstellar guest enters from a southern latitude, hugging declinations that northern sights barely skim above the horizon, your detection odds drop unless the southern network is in full stride. Think of it like lifeguards stationed on one half of a beach, swimmers wandering in from the far side, will be noticed later, and only if whistles carry that far. There is also the matter of background clutter. The southern sky hosts prime real estate. The Milky Way's bulge glows there with fields of stars so thick they look like poured sugar. That is gorgeous for postcards and complicated for moving dot hunts. A faint traveler passing against a crowded backdrop is a needle in a glitter factory. Software can subtract stars and compare frames, but the denser the field, the more ghosts appear, and the more false alarms chew up time. A survey might sensibly dial back sensitivity in those regions to avoid drowning in artifacts, which means you risk missing the faintest early glimpses of a new arrival until it brightens. Cadence, the rhythm of revisiting the same patch, is the unsung hero and the source of bias. Fast objects reveal themselves by shifting between snapshots taken minutes to hours apart. If a southern patch only gets one look on a given night, while a northern patch gets 3, the odds tilt. Double the returns, double the chance you notice a sprinting speck that was not there yesterday. When our visitors' first footsteps landed on southern tiles with thinner cadence, the discovery clock started at a disadvantage. Then there is the horizon trap. From a northern mountain, a southern intruder can hang low, swimming through more air and light pollution, making it harder to measure or even see. Low-altitude observations also suffer from distortion that smears the dot and hides subtle motion. You can catch it, but you might catch it later, and later can mean the difference between naming it early and learning about it after it has already strutted past the best angles. So are we missing a whole population because our biggest eyes stare north more often? The honest answer is that selection effects are real, and they nudge our sample in sneaky ways. If your net has wider holes in the south, you will undercount southern arrivals. If you revisit northern fields more frequently, you will overrepresent objects that pass that way. The universe is not biased. The map on your wall is. Fix the map. Add more southern coverage, smooth out cadence, clean up crowded fields with clever algorithms, and the census changes. The good news is that the fix is underway. Southern survey capacity has grown with wide-field cameras that can sweep enormous sky stripes each night. Networks coordinate between hemispheres better than ever, handing off targets like relay teams so no one drops the baton at dawn. Amateur and citizen telescopes in the south increasingly fill gaps, nabbing early confirmations when big facilities are weathered out. And on the software side, machine learning now helps separate real movers from crowded field ghosts with a confidence that would have sounded like science fiction a decade ago. Photosynthesis is plants' way of saying we invented solar panels first. Coordinated surveys are astronomers' way of saying we invented sky spam filters. There is a second, subtler bias, storytelling. Northern discoveries dominate headlines because many media hubs sit above the equator and time zones favor press cycles there. A southern first light can arrive while editors sleep, and by the time the story wakes, the freshest angles have moved on. That is not physics. It is sociology, but it shapes which arrivals feel surprising. Here is the punchline. A southern sky surprise was not the universe hiding anything. It was the mirror showing us our own blind spot. When an interstellar visitor steps out of the southern wings, we either catch it with a nimble network or we learn, again, that our spotlight needs a wider sweep. Either way, the lesson is healthy. The sky is big. Our attention must be bigger. Next up, Chapter 11 turns to the panic button and releases it gently. How closest is still very far. Why dramatic graphics make our hearts race, and how to read safe miss distances without spilling your coffee. Chapter 11, Debunk Corner. No, it is not coming for us. Let us take a deep breath together, because the internet forgot. A headline shouts that the interstellar visitor will make its closest approach, and suddenly, half the timeline is packing go bags while the other half is filming the sky like it owes them rent. Here is the calm version. Closest does not mean close. In space talk, closest usually means still very far, but this is the smallest big number we will see. Earth is basically a rock that won the cosmic lottery. And part of the prize is that the universe gives us breathtaking shows from a very safe balcony. Think of distance like neighborhoods. Your friend says, "Hey, I am closest to your house tonight," and you find out they are in a different city, but on the same highway you live near. That is closest. Nobody is ringing your doorbell. Space distances are the ultimate different city situation. Even a near miss in astronomy is the kind of far that would make an airline sigh and add a fuel surcharge. When you see animations of an object swooping past Earth, those are not to scale. They are cartoons with dramatic body language. If the scale were honest, the Earth would vanish into a dot. The visitor would be a speck near a dot, and the caption would say, "Calm down." Why does the word closest sound scarier than it is? Because our brains love small words. Closest feels like next door, and graphics do not help. Many news visuals pull orbits tight, so everything fits in a phone screen. Lines look like threads under tension. Missed distances look like hair widths. In reality, you could stack many Earths across the gap. You could stack them, take a lunch break, and still have room for dessert. There is also the glow problem. A bright object in the sky feels big, heavy, and nearby. That is how our eyes survived the savannah. If it looks big, it might be a bison or a storm. In space, brightness is a trickster. Comets can flare and grow tails that seem to wave hello, but that waving happens in sunlight, not at your doorstep. Gas and dust are shining and scattering light across unbelievable stretches. A dramatic sky does not equal danger. It equals sunlight meeting stuff that used to be asleep. Another anxiety seed is the change in speed near the sun. The visitor appears to speed up, angles shift quickly, and tracking apps draw curvier lines by the day. It feels like the plot is thickening. What is really happening is gravity doing its roller coaster routine. Inward, faster, outward, slower. Overall, the same long-range story you heard in earlier chapters. In for a brief hello, out for a long goodbye. There is no hidden steering wheel under the hood just because the curve got lively. You might also hear whispers about impact scales and color-coded threat levels. Those exist to assess rocks that actually cross Earth's path, and even then, the standards are painfully conservative. They are not theatrical alerts. They are boring, careful bins where boring, careful numbers go to do their job. Interstellar visitors on open routes do not even get past the bouncer at the door of those scales, because their lanes are not Earth lanes. If you see a frightening number dumped into your feed without context, treat it like a food label someone ripped off the wrong product. Let us address the second wave of panic. But what about fragments? What if a piece breaks off and hits us? Comet fragments are like popcorn kernels. They are exciting inside the bag. Outside, they are tiny. A fragment that breaks free still follows the same overall traffic pattern, unless a very specific and strong push sends it on a wildly new path. And even then, the night sky is an arena where gravity and time dilute drama. The odds that a random chip suddenly decides to take a beeline to your backyard are so small that insurance companies would laugh at you if you tried to add it to your policy. Shooting stars you see on random nights are not pieces of this visitor. They are all dust from old trails, harmless glitter burning up high above where planes fly. While we are at it, let us untangle the word approach. For many objects, the safe distance is measured from center to center. That is how astronomers keep it apples to apples. It makes animation arrows point to a comfortable gap that still appears tight if you ignore the scale. Imagine two cars in a parking lot. If you draw lines from steering wheel to steering wheel, the cars appear closer than if you count the empty space between bumpers. Space math uses the steering wheel version. Reality still has bumpers and a whole lot of asphalt. If you crave a number-shaped lullaby, here is the gentle truth wrapped in plain words. The visitor is not going to hit us. It is not going to graze us. And it is not going to do a surprise lane change after midnight. The path is charted by many teams from many places. When their predictions agree, that is confidence speaking, not a cover-up. Disagreement is loud and messy. Agreement is usually quiet. The quiet you hear is competence. There is one danger worth naming: misinformation. It spreads faster than any comet and leaves a longer tail. A cropped screenshot here, a misleading caption there, and suddenly your aunt is texting you about bunkers. The cure is not cynicism, it is curiosity. Ask where a number came from. Ask whether a graphic is to scale. Ask if the word closest hides a dictionary of context. 9 times out of 10, the answer lowers your heart rate and raises your appreciation for how good we have gotten at watching the sky. Here is the grin. Earth is basically a rock that won the cosmic lottery. And one of the jackpots is that our cosmic neighborhood is roomy. We can host a spectacular flyby and still have more than enough elbow room to stretch. So enjoy the show. Take a photo. Brag to future you that you watched an interstellar traveler pass by while your coffee was still warm. Next up, Chapter 12 puts on heat-resistant oven mitts and handles a spicy topic with care: the alien tech theory. We will grill it, season it with evidence, and serve it beside a generous helping of how you would actually test such an extraordinary claim. Chapter 12, the alien tech theory. Grilled gently. Every time a strange traveler crosses our sky, the same spark jumps the gap. What if it is not natural? The public claim usually arrives in 2 flavors. Flavor 1 says the object moves in a way that does not look fully explained by gravity and sunlight. Therefore, perhaps it is a probe with gentle engines, the cosmic equivalent of a hybrid car on eco mode. Flavor 2 points to appearances, an odd brightness pattern, an unusual color, or a tail that seems to come and go, and asks if that could be the glint of panels or a shell of engineered material. On cue, the idea blooms across comment sections. Maybe it is scouting, maybe it is listening, maybe it is a message in a bottle with very fancy handwriting. Before we carry the bottle to a museum, mainstream astronomers do something very unromantic and very important. They check whether the ordinary can explain the extraordinary looking. The simplest explanation that matches evidence is the one to beat. That means testing familiar culprits first: gas jets, sunlight pressure on low-density material, and thermal effects that nudge a path without any secret thrusters. If measured positions become more predictable after you add those known gentle forces, then the case for engines gets weaker, not stronger. Brightness behavior is a favorite battleground. A technological surface might flash like a mirror when the angle is just right, giving clean, repeatable sparkles. A small natural body, by contrast, tends to brighten and fade with a mix of rotation, roughness, and changing gas production, which looks messy rather than metronomic. If the light curve shows a tidy, clock-like pattern over many nights and many viewing angles, that would be intriguing. If it looks like a jazz solo, complex, evolving, sometimes loud, sometimes soft, then we are probably hearing a rocky drummer with a patchy surface and a few unruly vents. Color and polarization are next under the lamp. Engineered alloys or layered foils could scatter light in sharp, distinctive ways. Nature loves fuzzy edges. When observers measure how light is polarized after bouncing off dust, they usually find signatures that match fluffy aggregates and carbon-rich coatings. If someone shouted spacecraft, the counterpoint is simple. Show a spectrum or a polarization curve that looks like polished metal or laminate, not like toasted organics. Weird light does not equal a spaceship. It equals unusual fluff that spent a long time in deep cold and harsh radiation. Now let us speculate responsibly. Suppose you wanted tests that would even hint at engineering. What would you look for? First, maneuvering that refuses to rhyme with sunlight. Real outgassing is married to heating and rotation. It waxes when the active side faces the sun, wanes when it sleeps, and evolves slowly as vents open or clog. An engineered push could break that marriage. If the path changed at times when no part of the body was warming, or if it shifted in crisp steps with pauses between, that would be eyebrow-raising. Think of a swimmer who keeps surging in a pool even when the water jets are off. Second, specular glints that repeat like a metronome. A flat panel spins and throws back clean, bright flashes at regular intervals that persist as geometry changes. Nature can sparkle, but it is more like glitter than a lighthouse. If the sparkles line up with a fixed period across different phase angles, you might start whispering the words engineered surface under your breath. Third, narrowband emissions. A probe that talks might pick a tidy sliver of the radio spectrum. Space is full of static, but most of it is broad and noisy. A narrow, persistent, repeating tone locked to the object's sky position would be a showstopper. That is the kind of test radio observatories can do while the object is bright enough to track, and it comes with a clear yes or no. Either there is a tone or there is not. Fourth, thermal behavior that looks designed. Natural bodies warm and cool in ways set by porosity, spin, and sunlight. A craft might shed heat on purpose, keeping parts within friendly temperatures. Infrared observations that found a smooth, regulated thermal pattern, out of step with the messy solar input, would be curious. Bonus points if the pattern suggested radiators turning on and off. Fifth, material fingerprints. Spectroscopy can sometimes pick out molecules on the surface or in the gas. If you saw lines that shouted refined alloys, paints, or plastics that do not form in space, that would be hard to explain away. In practice, this is a tall order for a small, faint target, but it is on the wish list. Sixth, radar structure. If a close pass allowed planetary radar to ping the object, a crisp, angular shape would raise questions. Nature makes shards, sure, but a repeating lattice or a boxy silhouette would be odd. Most of the time, these visitors are too far or too faint for radar, but if you could, you would absolutely try. Seventh, purposeful course changes that conserve fuel-like behavior. A brief push aligned with an efficient direction, followed by a long coast exactly as a thrifty spacecraft would plan, would feel deliberate. Outgassing prefers the sun angle, not the nav textbook. Mainstream counterpoints to the alien tech claim are grounded in the track record of comets and small bodies. We have seen non-gravitational nudges many times and matched them with heating. We have watched light curves that get messy because the surface is messy. We have measured polarization that screams porous grains, not polished panels. The catalogue of natural weird is deep. It earns the first pass at every mystery. And there is a humility to preserve here. Extraordinary claims deserve extraordinary care in testing, but they also deserve ordinary patience. A flyby object gives us weeks to months, not years. Instruments have to hustle. Clouds ignore our drama. Some tests cannot be done in time. The absence of a smoking gun is not proof of absence, but it is a clear sign to holster the fireworks until the sky forces our hand. A joke to keep us honest. Black holes delete browsing history permanently. Alien probes would at least leave a user manual. If there is a manual, we have not found the table of contents yet. What we have found is a set of clues that line up neatly with ice, rock, dust, sunlight, and the gentle physics of heating. That story is not dull. It is astonishing. A snow-dark pebble from another star system can whisper its origin through the way it brightens, the way it breathes gas, and the way it leans into the sun. That is a miracle without rivets. Next up, Chapter 13 zooms out in time. We will follow a possible billion-year itinerary through the galaxy. Sketch how a small body gets kicked free of home, and imagine the long, star-to-star wanderings that turned our visitor into a seasoned drifter. Chapter 13, A Billion-Year Traveler. Close your eyes and picture a tiny snow-dark world, no bigger than a mountain, coasting through the galaxy like a seed on the wind. It has no engine, no map, and absolutely no hurry. Stars rise and set not in hours, but in eras. Nebulae drift past like slow fireworks. The background changes so gradually that you would need the patience of geology to call it change at all. If this sounds like exaggeration, remember the timeline. We are talking about a traveler that may have wandered for hundreds of millions of years, possibly a full billion, which is longer than complex life has walked on Earth with ankles and opinions. Where did it start? Imagine a young planetary system somewhere in the galactic neighborhood. A star swaddled in a disk of gas, ice, and dust. That disk is a messy nursery where baby planets grow by swiping pebbles from each other. When bigger bodies begin to strut, gravity becomes a bouncer with a short fuse. Small, icy bricks near the outer regions get tossed, some inward to become comets, some outward into the deep freeze, and a lucky few are yeeted all the way out of the parent system entirely. Our traveler is one of those ejected castaways, a snowball that lost the tug of war and won a ticket to the wide Milky Way. Once free, it joins a population that does not belong to any one star. Think of a crowd of long-haul hikers moving through a vast, dim valley. The valley, in this case, is not empty. It is threaded with the galaxy's spiral arms, star clusters, and gas clouds, all of it stirring under the influence of the Milky Way's mass. Move slow enough, and the galaxy's big structures become the weather. Move long enough, and you start to notice the neighborhoods. Astronomers talk about 3 big neighborhoods: the thin disk, where the sun lives on a pretty flat lane; the thick disk, a puffier layer of older stars with slightly different motions; and the halo, a sprawling, faint realm where ancient stars and dark matter keep to their own counsel. A small wanderer can drift among these populations depending on the push it received at birth and the bumps it collects along the way. If our traveler shares the motion and tilt of the thick disk, it would be in good company with stars that are older and more seasoned, the elders who have seen a few spiral arms come and go. Thick disk membership would not make it noble, just experienced. What happens during a billion years of cruising? Close passes do. The galaxy is a generous place for near misses. Every so often, the snowball slides within a few light years of another star. Gravity nods. The path tilts by a tiny angle, and the long road continues. Most passes are polite, the celestial version of 2 ships trading brief horn blasts on a foggy night. But every million years or so, the odds deliver a closer encounter. A strong tug at the right moment can change the tilt more noticeably, sending the object into a new lane that will only reveal its difference after the next few 100 million years of patience. Gas clouds also have a say. They are not brick walls, they are velvet curtains. Move through a diffuse cloud, and the snowball surface collects an additional coat of cosmic seasoning. Radiation in the galaxy is relentless, knitting simple molecules into darker, stickier films. Over eons, that surface becomes a scrapbook, thin layers recording starlight, particle storms, and the occasional dusting by a passing cloud. That is why many small, icy bodies wear a dark, reddish coat. It is not paint, it is time. Now zoom out even farther, to the grand carousel of the Milky Way. The entire disk rotates, but not like a vinyl record. Different parts move at different speeds. Spiral arms are patterns rather than solid arms, and stars bob up and down through the disk like dancers, improvising to a very slow beat. Our traveler rides this music, its orbit around the galactic center, stretching across hundreds of millions of years. During that time, it might pass above and below the main plane, a gentle oscillation that carries it through different neighborhoods. If it really is a thick disk drifter, that vertical bob is part of its signature dance. It is tempting to imagine loneliness here, but the cosmos does not leave wanderers bored. Starlight comes and goes. The glow of the galaxy is a permanent horizon. A nearby supernova might flash once in a very long while, scribbling a bright exclamation point across the dark. Tidal nudges from the general galactic mass whisper tiny course corrections that add up only over epochs. From the snowball's perspective, this is normal life. From ours, it is a travelogue written in patience. Eventually, chance steers the wanderer into the outskirts of our solar system. The sun is just another porch light in the fog until the path angles close enough for a greeting. The long sleep begins to end. Distant sunlight licks the surface. A few early molecules stir, and the story you and I have been following begins its quick, bright chapter. Quick for us, anyway. For the traveler, this is just a warm blink in an otherwise cold biography. There is something humbling in that time scale. While this snowball toured the Milky Way, Earth went from single-cell snorkeling in ancient seas to creatures that argue on the internet. Forests rose and fell, continents drifted, and languages were born, all while our visitor kept gliding in a silence wider than any poetry. Black holes may delete browsing history permanently, but interstellar snowballs keep their own records in ice and dust, and they do not care about our comment sections. So, when you look up and see a photon that left the sun bounce from the skin of this ancient drifter and land in a camera, you are seeing a page from a book that started long before there were readers. In that page, there are clues about the birthplace, deep cold, gentle assembly, and a shove from youthful planets. There are hints about travel companions, old stars moving with thick disk swagger, and there is a promise that more wanderers are out there, passing in the dark, each with its own billion-year plot. Next up, Chapter 14 trades time for perspective. We will explore how our particular seat in the cosmic theater can make perfectly normal paths look suspiciously aligned, and why your eyes sometimes misread the dance when you watch from a moving balcony. Now continue to Chapter 14, Alignment Illusions. Why paths look suspicious. Explain ecliptic alignments, observational geometry, and why our vantage point can make a normal route look too tidy. Use simple analogies. Highway lanes, seen from an overpass, can make different cars look like a convoy. Stretch it into a full 700, 800-word deep dive, with zero repetition from any future or previous chapter. Chapter 15, What the Cameras Cannot See. Every sky picture you love is a negotiation. On one side, the universe, sprawling and patient. On the other, detectors that get tired, lenses that sweat dew, and a planet that insists on spinning while you are trying to stare. Space does not lean in for a selfie. It glides by at its own pace, and our cameras do their best with the angles and the weather they are handed. Today's chapter is about the things that fall between frames, the parts the pictures cannot quite hold, and why that is not a scandal, but the ordinary cost of doing astronomy in a moving, breathing world. Start with viewing angles. We never get a director's crane shot of the solar system. We observe from one small world on a tilted path around the sun, at times borrowing a look from spacecraft that orbit other worlds, each with their own constraints. That means some lines of sight are easy and some are awkward. If a target hugs the sun from our point of view, it sinks into glare. If it sits low over the horizon, we peer through thick, wobbly air that makes stars shimmy and turns small objects into fuzzy smudges. Even with the best tracking, a fast traveler can drift across the detector faster than you would like, stretching into a streak that smears away detail. To a camera, that is the difference between a face and a motion blur. Then there is dust, both cosmic and homegrown. In space, a comet sheds a gauzy cloud that reflects sunlight and muddies our measurements. The brightness we record becomes a stew, some from the solid nucleus, some from the gas that surrounds it, some from dust shining like powdered charcoal tossed into a sunbeam. On Earth, the air adds its own mischief. Wind kicks grit across a dome, a nearby wildfire perfumes the sky with haze. Humidity softens focus, like a romantic filter that no astronomer asked for. Even in orbit around another planet, thin clouds and high dust in that planet's atmosphere can scatter light just enough to hide a dim target. Entropy loves mess, and the sky is not shy about collaborating. Cameras themselves have personalities. Detectors saturate if a bright star lands on the wrong pixel. Subtle electronic ghosts can echo a glittering satellite across the field of view. Temperature swings nudge focus. A single hot pixel, left uncorrected, impersonates a tiny asteroid better than your most creative prankster friend. This is why astronomers dote on calibration frames, the way chefs fuss over mise en place. You take pictures of darkness to measure the detector's own glow. You take pictures of an evenly lit surface to understand how each pixel behaves. You track stars with known properties to check that tonight's system is telling the truth. Astronomy runs on coffee and calibration in nearly equal portions. Even with careful preparation, the clock beats us, the target sets. The moon rises and floods the field with silver noise. A gust closes the dome. A spacecraft enters a scheduled downlink that pushes your observation to the next orbit. The cadence hiccups, and suddenly there is a gap of hours or days where the object kept moving, but we did not catch it. Those gaps matter. When you draw a path through space from a string of positions, missing beads mean the string can wiggle in more ways than you prefer. That wiggle room shows up as generous error bars, the little whiskers on plots that admit, with refreshing honesty, that the answer is a range, not a single heroic number. Generous error bars do not mean someone is hiding anything. They mean the team refused to pretend the camera saw more than it did. If you have ever tried to estimate when a friend will arrive based on 2 text messages and a shrug, you already understand the principle. 2 data points can only anchor a line so tightly. Add a third point, and the window narrows. Add 10, and you start sounding confident. Science treats uncertainty like a living thing that shrinks when you feed it with observations and grows when you starve it. Another quiet limit is dynamic range. The same exposure that captures a faint tail might blow out the bright inner region. If you set the camera to spare the core, you risk losing the wispy edges. Observers split the difference with sequences of short and long shots, and later stitch them into a fuller portrait. That stitching is art and discipline, not deception. It is the only way to show a scene that spans both a floodlight and a candle. Tracking brings its own trade-offs. You can guide the telescope at the rate the stars appear to move, keeping background points crisp while the object streaks, or you can track the object, freezing it and letting the stars smear into lines. Each choice answers a different question. Do you want accurate positions among familiar star patterns? Or do you want the sharpest possible look at the traveler itself? You cannot have both at once. The internet prefers a single perfect picture. The sky offers a menu of imperfect but useful ones. Statistical noise is another party crasher. Photons arrive like raindrops in a brief shower. Sometimes a little clump, sometimes a lull. When targets are faint, that randomness matters. It makes repeated measurements wobble, even with identical settings. The cure is not to declare defeat, but to gather enough frames that the wobble averages out. Stack many images, and the real signal rises like a shoreline at low tide. But stacking takes time that fast. Objects are not always willing to grant. So how does science handle all this without sweeping the mess under the rug? By making the rug transparent. Teams publish their methods, list their assumptions, and attach the error bars right next to the headline numbers. They revise predictions when new data arrive and label the revisions clearly. They keep raw images in archives so others can recheck the math and even find earlier, accidental snaps hidden in old fields. When 2 groups disagree, the disagreement is not treated like a scandal. It is treated like a lead. Who measured what, when, and how? Which angle suffered from glare? Which camera had a quirk that week? The answers pull the error bars toward each other until they overlap like a handshake. If you want an image that captures the spirit of the work, picture a chalkboard that is never erased, only written over more neatly each day. Yesterday's numbers are not lies, they are drafts. The next observations sharpen the handwriting. The script advances from pencil to ink, not because someone forced the plot, but because the cameras, within their limitations, kept showing up. Next up, Chapter 16 turns those limits into a detective story, following the tiniest lawful pushes, sunlight, warmth, and breathy jets, and showing how a handful of gentle forces can, over days, tilt a traveler's path in ways that our newly honest error bars can see. Chapter 14, Alignment Illusions, Why Paths Look Suspicious. Have you ever stood on an overpass and watched traffic below? From that height, 4 different cars in 4 different lanes can look like a military convoy if they happen to line up for a second. They are not conspiring. Your angle is space plays the same trick. When we plot an interstellar traveler's route on a flat screen from our moving perch, perfectly normal geometry can look suspiciously tidy, like the cosmos ironed the line before sending it to social media. First, the stage, the ecliptic. Picture the solar system as a giant dinner plate with most of the crumbs on the same plane. Planets orbit in this plate. Many asteroids prefer it, and a lot of our charts are drawn with this plate as home base. Now, add us. Earth is riding the rim, circling once a year, turning that plate into our reference frame for everything. Any path that slices near the plate, even at a healthy tilt, will project as an elegant sweep when you flatten the view. Take a hula hoop, hold it in front of your face, and tilt a pencil through it at an angle. From the right angle, that pencil's line looks uncannily aligned with the hoop, even when it is nowhere near parallel in 3 dimensions. Projection is a stealthy artist. A 3-dimensional arc, when thrown onto a 2-dimensional canvas, can masquerade as a cleaner shape than it really is. Think of airplane routes on a world map. A great circle that is truly the shortest path looks like a curve that hugs strange latitudes. No pilot is hiding a detour. Your flat map is. Sky maps do this to orbits. They compress depth, they stretch edges, and they whisper, "Look how straight that curve is," when the real motion is a graceful bend through space. Then there is foreshortening, the cousin of projection. Hold a pencil straight out in front of you. It appears short. Tilt it sideways, suddenly it looks longer. Paths that cross our sightline head-on appear tighter and more direct than paths that sweep sideways, even if both are equally complex in 3 dimensions. If you film a skateboarder rolling straight toward your camera, the route looks like a single line painted on the pavement. Switch to a balcony view, and you finally see the S-curve they traced. Space rarely gives us balcony seats. We mostly watch from the sidewalk. Our own motion turns these visual quirks into full-blown illusions. Earth orbits the sun while spinning, so our viewpoint shifts every hour and every month. That means the background stars slide a little, and moving objects appear to change direction in ways that feel dramatic from the ground. Astronomers correct for this with careful math, but uncorrected plots shared online can look like the object twitched on cue. It did not. We changed seats during the show and accused the actor of improvising. Retrograde motion is a classic example. Planets occasionally seem to reverse direction against the stars because we pass them or they pass us, the same way a slower car looks like it is moving backward when you overtake it on the highway. Interstellar visitors can display a flash of that same apparent reversal or a sudden speed up when our track around the sun lines up just so. It is not a secret thruster. It is the camera operator jogging sideways while filming. Even the word aligned is a trap. On a chart, alignment implies a shared plan, like geese in formation. In space, aligned with the ecliptic often just means the projection falls near the plate from our current vantage. That is expected, because the plate is where our surveys stare most often. We draw our maps with the plate centered. We tile our nights along it, and we color our heat maps to favor it. When a traveler's projected path hugs that lane, it is not suspicious. It is statistically likely that our charts will make it look that way. Parallax adds another layer of mischief. When your 2 eyes view your hand at arm's length, you perceive depth because the view shifts between left and right. The Earth-Sun system is a gigantic version of that. As we circle the sun, our baseline changes, and nearby objects appear to slide relative to distant stars. For a fast passerby, that slide is noticeable over days. If you draw the object's position without accounting for this yearly baseline, the dots line up in a way that whispers, "Someone planned this. Someone did." Geometry, bright tails and comey can fuel the illusion. A comet's tail points away from the sun, not along the direction of travel, like a windsock that cares only about where the wind comes from. If the tail happens to overlay the projected path on your chart, Your brain connects the two and decides the traveler is following its own glow. It is not. The tail is a weather vane, not a lane marker. It can make a normal route look precise because the line of light and the line of motion happen to share a frame in a way that flat charts amplify. Timing multiplies the effect. Observations cluster when an object is brightest, or when weather favors certain longitudes. That means the plotted dots you see online often come from a handful of nights with similar geometry. Unintentionally, you are looking at snapshots taken from the same side of the dance floor. Change the angle, add southern observatories, add a later week, add a dawn sequence, and the tidy line becomes a fuller arc that looks less like choreography and more like what it always was, a natural, unbound swing. If you want an everyday sanity check, try this. Watch two planes crossing the sky at very different altitudes. For a few seconds, they can appear to trace the same path edge to edge, even though one is many kilometers above the other and heading to a completely different city. No pilot is hiding a rendezvous. Your angle stacked 2 stories into one line. The sky above your head is an overpass, and you are the person saying, "Look, a convoy," when 3 strangers just happened to share a lane from your viewpoint. None of this dilutes the wonder. Understanding why paths look tidy does not make them less beautiful. It makes the beauty honest. The universe is not leaving clues in calligraphy for us to decode. It is following the rules of motion, while our eyes and charts do their best to keep up. Once you learn the trick, the rumor of secret alignment becomes a teachable moment, a chance to explain plates, projections, parallax, and the moving balcony we sit on. Next up, Chapter 15 leans into the limits, what the cameras cannot see, how dust and glare hide details, and why big error bars are not excuses, but invitations to collect smarter, better data. Chapter 15, What the Cameras Cannot See. Every sky picture you love is a negotiation. On one side, the universe, sprawling and patient. On the other, detectors that get tired, lenses that sweat dew, and a planet that insists on spinning while you are trying to stare. Space does not lean in for a selfie. It glides by at its own pace, and our cameras do their best with the angles and the weather they are handed. Today's chapter is about the things that fall between frames, the parts the pictures cannot quite hold, and why that is not a scandal, but the ordinary cost of doing astronomy in a moving, breathing world. Start with viewing angles. We never get a director's crane shot of the solar system. We observe from one small world on a tilted path around the sun, at times borrowing a look from spacecraft that orbit other worlds, each with their own constraints. That means some lines of sight are easy and some are awkward. If a target hugs the sun from our point of view, it sinks into glare. If it sits low over the horizon, we peer through thick, wobbly air that makes stars shimmy and turns small objects into fuzzy smudges, even with the best tracking. A fast traveler can drift across the detector faster than you would like, stretching into a streak that smears away detail. To a camera, that is the difference between a face and a motion blur. Then there is dust, both cosmic and homegrown. In space, a comet sheds a gauzy cloud that reflects sunlight and muddies our measurements. The brightness we record becomes a stew, some from the solid nucleus, some from the gas that surrounds it, some from dust shining like powdered charcoal tossed into a sunbeam. On Earth, the air adds its own mischief. Wind kicks grit across a dome. A nearby wildfire perfumes the sky with haze. Humidity softens focus like a romantic filter that no astronomer asked for. Even in orbit around another planet, thin clouds and high dust in that planet's atmosphere can scatter light just enough to hide a dim target. Entropy loves mess, and the sky is not shy about collaborating. Cameras themselves have personalities. Detectors saturate if a bright star lands on the wrong pixel. Subtle electronic ghosts can echo a glittering satellite across the field of view. Temperature swings nudge focus. A single hot pixel, left uncorrected, impersonates a tiny asteroid better than your most creative prankster friend. This is why astronomers dote on calibration frames, the way chefs fuss over mise en place. You take pictures of darkness to measure the detector's own glow. You take pictures of an evenly lit surface to understand how each pixel behaves. You track stars with known properties to check that tonight's system is telling the truth. Astronomy runs on coffee and calibration in nearly equal portions. Even with careful preparation, the clock beats us. The target sets. The moon rises and floods the field with silver noise. A gust closes the dome. A spacecraft enters a scheduled downlink that pushes your observation to the next orbit. The cadence hiccups, and suddenly there is a gap of hours or days where the object kept moving, but we did not catch it. Those gaps matter. When you draw a path through space from a string of positions, missing beads mean the string can wiggle in more ways than you prefer. That wiggle room shows up as generous error bars, the little whiskers on plots that admit, with refreshing honesty, that the answer is a range, not a single heroic number. Generous error bars do not mean someone is hiding anything. They mean the team refused to pretend the camera saw more than it did. If you have ever tried to estimate when a friend will arrive based on 2 text messages and a shrug, you already understand the principle. 2 data points can only anchor a line so tightly. Add a 3rd point, and the window narrows. Add 10, and you start sounding confident. Science treats uncertainty like a living thing that shrinks when you feed it with observations and grows when you starve it. Another quiet limit is dynamic range. The same exposure that captures a faint tail might blow out the bright inner region. If you set the camera to spare the core, you risk losing the wispy edges. Observers split the difference with sequences of short and long shots, and later stitch them into a fuller portrait. That stitching is art and discipline, not deception. It is the only way to show a scene that spans both a floodlight and a candle. Tracking brings its own trade-offs. You can guide the telescope at the rate the stars appear to move, keeping background points crisp while the object streaks. Or you can track the object, freezing it, and letting the stars smear into lines. Each choice answers a different question. Do you want accurate positions among familiar star patterns? Or do you want the sharpest possible look at the traveler itself? You cannot have both at once. The internet prefers a single perfect picture. The sky offers a menu of imperfect but useful ones. Statistical noise is another party crasher. Photons arrive like raindrops, in a brief shower, sometimes a little clump, sometimes a lull. When targets are faint, that randomness matters. It makes repeated measurements wobble, even with identical settings. The cure is not to declare defeat, but to gather enough frames that the wobble averages out. Stack many images, and the real signal rises like a shoreline at low tide. But stacking takes time that fast. Objects are not always willing to grant. So how does science handle all this without sweeping the mess under the rug? By making the rug transparent, teams publish their methods, list their assumptions, and attach the error bars right next to the headline numbers. They revise predictions when new data arrive and label the revisions clearly. They keep raw images in archives so others can recheck the math and even find earlier, accidental snaps hidden in old fields. When 2 groups disagree, the disagreement is not treated like a scandal. It is treated like a lead. Who measured what, when, and how? Which angle suffered from glare? Which camera had a quirk that week? The answers pull the error bars toward each other until they overlap like a handshake. If you want an image that captures the spirit of the work, picture a chalkboard that is never erased, only written over more neatly each day. Yesterday's numbers are not lies. They are drafts. The next observations sharpen the handwriting. The script advances from pencil to ink. Not because someone forced the plot, but because the cameras, within their limitations, kept showing up. Next up, Chapter 16 turns those limits into a detective story, following the tiniest lawful pushes, sunlight, warmth, and breathy jets, and showing how a handful of gentle forces can over days tilt a traveler's path in ways that our newly honest error bars can see. Chapter 16: Tiny Forces, Big Consequences. If the universe had a volume knob, tiny forces would live in the quiet end of the dial. You hardly notice them at first. Then you play the song long enough and realize the background harmony has been steering the melody all along. Small pushes matter in space because space is patient. Give a traveler a whisper of nudge, let it run for days, and you get a path that drifts just enough to make careful people reach for fresh coffee and sharper pencils. Start with sunlight pressure, the politest shove in the cosmos. Light carries momentum, which is a fancy way to say photons are small messengers who bump into surfaces and refuse to apologize. Each bump is laughably gentle, like a gnat tapping your sleeve, but gnats do not quit. Over long stretches, the sum of the taps can lean on a small object and ever so slightly bias its motion. If the surface is bright and feathery, the effect is stronger. If it is dark and compact, weaker. Imagine standing in a breeze that barely stirs your hair, then wearing a giant sail hat. Suddenly, you notice the wind. Sunlight is that breeze. Dust crust and fluffy grains are the hat. Next comes thermal effects, the slow cooker of orbital mechanics. When one side of a body warms in daylight and cools in darkness, it re-radiates heat a little more in certain directions. That thermal sigh creates a minuscule thrust. Think of a spinning rotisserie chicken of ice and dust. The day side warms, the evening side releases a touch more heat, and the whole snack experiences a tiny push that lines up with the time of day. Not enough to make dinner fly off the spit, but enough that, over many rotations, the direction of travel feels a nudge. The details depend on how fast it spins, how porous the surface is, and how quickly heat seeps under the skin. Chalk it up as the world's gentlest jet engine, powered by afternoon warmth. Then there is jet torque, the rambunctious cousin. When sunlight wakes subsurface ices, gas jets can fire from patches that face the sun. If the object spins, those patches swing in and out of light, turning the jets on and off like sprinkler heads on a rotating lawn. Each burst does two things. It pushes a little on the path, and it twists the body, either speeding the spin or slowing it, sometimes even tipping the spin axis over time. The twist matters because it changes which patches get favored in the next round of heating, which then changes the direction of the next round of pushes. It is feedback with rhythm. If you have ever tried to paddle a canoe while it yaws, you know the feeling. A push here becomes a turn there, and the next push lands on a new heading. So how do tracking teams separate these quiet harmonies from noise? And how would they spot a genuinely hidden force if one was secretly at work? First, they listen for the beat. Sunlight pressure and thermal size follow the sun. Their direction is tied to where the star is in the sky, from the object's point of view, and their strength grows and fades smoothly with distance. Jet-driven nudges dance with the rotation period. That means the residuals, the tiny differences between predicted and measured positions, tend to curve gently and predictably. If the curve tightens when you add a sun-tied push, you are hearing the right music. If you fold the data by the rotation period and the wiggles line up, you have probably caught jet torque in the act. Second, they test out of sample, fit your model on last week's measurements, then predict tonight and tomorrow. If your recipe includes the right small forces, the object lands in the center of the camera more often than not. Miss a force, and the target arrives off to the side, like a guest who misread the invite. The best part is that the sky does not care which team is guessing. Independent groups using different software can compare where their predictions agree and where they wander. Agreement means you probably captured the quiet pushes correctly. Third, they triangulate with many eyes. Observatories at different longitudes, latitudes, and altitudes watch the same traveler. Parallax, atmosphere, and local quirks are all different, but the physics is the same. A real small force leaves a common signature in all datasets once you correct for the vantage point. A fake pattern, say, a camera quirk that only one system suffers, will not repeat elsewhere. That cross-check is the astronomer's lie detector. Now the fun part, the what if. Suppose a hidden force were real, not the lawful sunlight and jet stuff, but something smarter or stranger. What would it look like? You would see timing that breaks the sun's rhythm. Natural pushers love daylight. If the path started shifting at hours when the active side was not illuminated, that would raise eyebrows. Pattern 1. Offbeat nudges, happening during expected lulls. You would see steps rather than smears. Natural effects are gradual. A secret push might look like a series of discrete kicks, followed by steady coasts. Pattern 2. Stair-step residuals, as if someone tapped the thruster for a moment and then let the object glide. You would see direction changes that ignore the sun. Sunlight pressure points away from the star. Jets prefer the afternoon of the rotating body. A hidden force could favor a fixed inertial direction, like always pushing north regardless of daylight. Pattern 3. A stubborn vector that stays put while the sun angle swings. You might see a light curve that refuses to cooperate. Natural surfaces brighten and dim with rotation and distance, sometimes messily, but always with a physical link to heating. If the brightness stayed eerily flat, while the path kept getting gentle shoves, you would wonder how the push is happening without any sign of gas or dust. Pattern 4. Motion without matching breath. How would teams catch such a mischief maker? By tightening the net. Increase cadence so that hours do not go unmeasured. Monitor rotation with rapid, precise photometry to know when daylight should matter. Coordinate radio or infrared campaigns to look for telltale outflows or warm spots. If the path shifts but the vents are silent and the thermal map is dull, you circle the anomaly in red. Compare independent orbit solutions nightly and do blind predictions where one group hides its newest data while another forecasts. If the hidden force is real, everyone's forecasts will miss in the same new direction until they include a term that has nothing to do with sunlight or spin. In short, tiny forces are not plot twists. They are the plot. We can write them in plain words and watch them shape the ending, one quiet push at a time. And if something truly odd ever joined the cast, it would leave footprints that do not match the sun's schedule, the rotation's drumbeat, or the infrared's warm whisper. That is the kind of mystery the sky itself will help solve, one honest measurement at a time. Next up, Chapter 17 looks at another human force, the publishing pipeline. Why do images and numbers sometimes arrive later than your feed desires? And how does science balance speed with accuracy without feeding the rumor machine? Chapter 17. Are agencies hiding data or just processing it? There is a moment in every space story when the public feed goes quiet. Images do not drop, numbers do not update, and the comment section starts pacing like a cat near a closed door. They are hiding something, someone declares, as though mission control were a dragon sitting on a treasure hoard of pixels. Today, let us open that door and show what usually lives behind it. Not secrecy, but workflow. It turns out space science is less cloak and dagger and more coffee and checklists. Start with embargoes, the word that sounds like a spy novel, but mostly means let us all talk at the same time. An embargo is a temporary agreement between scientists and reporters. The team shares a forthcoming result under the promise that coverage will wait until everyone has the full context and the paper is ready. Why bother? Because science is a team sport played across time zones. If one group posts an early slice and another posts the other half a week later, the public hears two halves of a sentence and spends days trying to guess the verb. An embargo nails the moment so the full story drops together. It is not a muzzle, it is a metronome. Peer review is the next character in our backstage tour. Think of it as a dress rehearsal, where the rival theatre company is invited to critique the lighting cues. Before results become part of the record, other experts read the methods, check the math, and ask annoying questions like, "Did you correct for that camera quirk on Tuesday?" This takes time. Reviewers have their own projects, real lives, and opinions about commas and calibration. The process is slow by design, because the goal is to trade instant applause for durable truth. The internet runs on minutes. Peer review runs on weeks to months. That mismatch can feel like silence from the outside, when inside, It is a very loud room full of equations and polite arguments. Now, what about spacecraft teams and their habit of holding imagery briefly? Picture this. A spacecraft stares, snaps a scene, and beams down data that looks like a jigsaw puzzle after a toddler has had a go. Raw images are not just pictures. They are arrays of numbers with hot pixels, cosmic ray hits, geometric distortion, and color channels that do not line up yet. Engineers and scientists run the data through pipelines that correct, calibrate, and document every step so that 6 months from now, another team can reproduce the same image and not discover a hidden gremlin. That work is not glamorous. It involves reference lamps, star fields with known brightness, and a lot of "are we sure that bump is real?" Holding an image for a day or a week is not a smokescreen. It is quality control. There is also the human factor. You will not see in a press release. Coordination. A single snap from a spacecraft might have implications for several research groups. Who leads? Who confirms the interpretation? Who checks that the draft caption does not imply more than the data can support? Space agencies try to avoid the scenario where one enthusiastic sentence locks in a mistake that takes months to unteach. They would rather show you a reliable picture tomorrow than an exciting myth today. Black holes delete browsing history permanently. Mistakes on the internet do the opposite. Contrast that with open programs and public dashboards, the places where you can watch the sausage get made while it is still being seasoned. Many survey projects post nightly candidate lists, raw thumbnails, and automated orbit fits with a digital version of a sticky note that says, "Work in progress." Those sites are marvelous, and they also require a specific kind of reader, someone who accepts that provisional means provisional. A dashboard that updates in near real time will sometimes show wild swings because a single cloudy night knocked out a chunk of data. The point is not to deliver polished conclusions every morning. The point is to let the community steer quickly, catch errors early, and pounce on fleeting opportunities. If you want to ride along, bring patience and a sense of humor. Earth is basically a rock that won the cosmic lottery. The lottery's fine print includes occasional maintenance messages. So are agencies hiding data? Occasionally, yes, but not in the scandal sense. There are legitimate cases where imagery stays internal for a short, defined period. Reasons include planetary protection protocols, privacy for targets that have not yet been confirmed, or agreements that give instrument teams a head start to harvest a few core results, in return for years of building and babysitting the hardware. These proprietary periods are measured in days to months, with clear sunset dates. After that, the vaults open and the archives become a buffet. You can download the files, rerun the pipelines, and if you are ambitious, find things the original team missed. That is not secrecy. That is delayed gratification with a published schedule. Transparency is not perfect, but it is better than the internet thinks. When data stay private forever, suspicion is warranted. When data wait their turn for calibration, cross-checks, and a go signal, suspicion is redundant. The difference shows up in the paperwork. Healthy projects publish timelines. Note what is provisional and list where to find the raw stuff once the dust settles. They correct mistakes in public with version numbers and change logs. If you want a litmus test, look for exactly that, version numbers and change logs. Conspiracies do not love change logs. Laboratories do. There is a simple way to live with the pace. Treat the quiet gaps as loading bars, not red flags. If an agency says, "Images pending calibration," they almost always mean, "We want future you to trust present us." If a dashboard says, "Predictions updated after new astrometry," that is transparency, showing its work. And if a paper arrives a month after a rumor thread, remember that the paper has to answer to posterity, while the thread only has to answer to tonight. Next up, Chapter 18 looks forward. We will ask how to be ready for the fourth interstellar guest, faster alerts, smarter follow-ups, and maybe one day a tiny sprinter mission that can dash out to meet a wanderer before it blinks and sails away. Chapter 18. After 3I, preparing for the next visitor. Every great story ends by handing the hero a better map. This interstellar cameo did more than give us pretty pictures. It rewrote our playbook. The next time a wanderer peeks over the horizon, we want our tools warmed, our checklist short, and our coffee already poured. Earth is basically a rock that won the cosmic lottery. Step 1 of spending those winnings wisely is to stop being surprised when the galaxy sends a guest without an RSVP. Start with triggers. Discovery used to feel like a doorbell that rang at random hours. Now the goal is continuous listening. Survey cameras feed alert streamers that never sleep, and the moment a dot moves in a way that whispers outsider, the network should chirp phones across continents. Imagine a triage board in the cloud, a traffic light that flips from green to amber when motion looks unbound, then to bright red when a second observatory confirms the arc. The moment red appears, a prepared list of targets and observers lights up. No hunting for email addresses. No midnight guesswork. Just a baton passed into running hands. Next, polarimetry and friends on standby. We learned how important fast texture clues are. If dust is fluffy, if grains are coated in dark organics, polarization will say so early, and that early read changes everything. Exposure times, filter choices, and what kind of models you bring to the first draft. Build a kit that can swing into place in minutes, not days. A simple polarimeter on a mid-sized telescope, a ready script for robotic instruments, and a short menu of standard stars to calibrate against. Think of it as a diner that never closes. Hot polarization, fresh spectra, and a side of photometry. Served to go, citizen telescopes deserve a star on the title card. When a target sprints and the weather plays diva, backyard observers and school roofs fill the gaps with stubborn patience. The next playbook reserves them real roles. A public dashboard should list the 2 or 3 most valuable next observations that a small scope can deliver tonight, a time window, a sky patch, and a recommended exposure. Hit those and you are not just taking a picture, you are shrinking the error bars that drive tomorrow's professional schedule. Photosynthesis is plants' way of saying we invented solar panels first. Citizen astronomy is humanity's way of saying we invented extra eyes. Coordination is the secret sauce. The plan is to rehearse like a fire drill, not improvise on the night. Once a quarter, teams could run a tabletop exercise, inject a fake alert into the system, let the bots shout, watch the telescopes pivot, and see where the chain squeaks. Did the Southern Hemisphere get the memo before sunrise? Did the radio observatory receive a clean slot? Did the archive assign a stable name so images from 5 continents did not scatter under 5 labels? The results become fixes, and the fixes become muscle memory. We also need smarter software referees. The first 10 minutes after an alert are a blur of plots that can mislead if you forget about perspective. Train ranking algorithms to discount bad geometry, to flag when a projected line looks suspiciously tidy because of our own viewpoint, and to suggest the next point that would most reduce confusion. Call it humility as a service, code that remembers we sit on a moving balcony. Now for a fun what if that is inching toward why not. Imagine a micro mission on permanent standby. No new rocket, just a ready-to-ride spacecraft that can hitch a lift on the next commercial launch, heading anywhere roughly useful. It weighs less than a small car, uses high-efficiency electric thrusters, and stows a compact camera, a simple spectrometer, and a polarimeter. The craft waits in a parking orbit. When the 4th interstellar traveler appears, and the geometry says a sprint can intersect the path, the micro-mission fires its engines for weeks, not years, and aims for a respectful, science-rich flyby. To make that real, you pre-bake everything that usually takes forever. You certify the avionics. You pre-write the command sequences for search, approach, and encounter. You stockpile public software, so raw images hit the ground with calibration attached. You even pre-negotiate the data policy, a short, clearly dated proprietary window for health checks, followed by automatic release to a shared archive with live thumbnails, so the world can ride along in honest, near real time. No hand-wringing, no reinvention, just go. Will a micro-mission catch every visitor? No. Space is a timing snob, but if it catches 1 in 10, or even 1 in 20, the payoff is time capsule level. A close look turns guesses about grain size into measurements. It changes probably water and carbon dioxide into here are the exact signatures at this distance, and that lighting. It maps the shape, listens for jets, and times the spin. The first close pass of an interstellar snowball would be the kind of scientific memory that generations point to and say, that is when we stopped just watching and started meeting. Between now and that sprint, we can make smaller moves that matter. Pre-approved target of opportunity time on key telescopes with a simple clause, if an unbound object is confirmed, the queue bends. Expand open pipelines so non-experts can help vet real candidates from false positives by clicking through short tutorials. Build classroom kits that let students measure a light curve in a single class period, turning curiosity into skill. And keep telling the story in plain words. Rumors grow in silence, clarity grows in daylight. The more people understand why lines look aligned, why tails point away from the sun, and why error bars are honest, the less oxygen there is for dramatic myths. The next traveler will arrive unbothered by our schedules. It will not pause for weekends, awards shows, or weather. That is fine. We can be ready. We can make the first hour count, the first day efficient, and the first week generous with shared data. And if a tiny sprinter really does leap from parking orbit to greet a wanderer between the planets, you and I will get to say we watched the moment a species that once only waited on cliffs learned to run down the beach and wave.